Hey, folks. All right. So, what we're doing here is going through some of the information that'll be important when you are completing Lab 1. The first lab of the semester, the first official lab, is on plate tectonics. And um, to make sure that everybody has the same information, again, the information that you'll need for the lab, we're going through a few slides to talk about plate tectonics. So let's get started. It lets me advance the slides. Okay. So plate tectonics is a relatively new theory in geology compared to some other foundational science that has been around for hundreds of years. Plate tectonics was really just accepted as a theory uh, in the 1960s, 1970s, which does sound like a long time ago now, but again, relatively speaking, it's fairly recent. The reason for that is because this theory actually did start um, further back in the past, but it was called something else at the time and was a little bit different. So, a um, scientist by the name of Alfred Wegener came up with the hypothesis of continental drift. And the main idea was that he proposed that continents moved or drifted through the oceans and had at one time been all together as one large supercontinent. He named it Pangaea and said that Pangaea began to break apart about 200 million years ago. To and are now in the positions that they are in today. Um, that theory wasn't immediately accepted because Alfred Wegener couldn't explain how continents could drift around in the ocean. But long story short, decades and decades later, past Alfred Wegener's time, unfortunately, the theory was eventually accepted, but as the theory of plate tectonics. And it was accepted because other scientists finally discovered the mechanism for how continents can move. And you'll surely go over more details about that in your lecture. But the short version is that there are processes going on in the ocean that we didn't know about until about the 1940s. And so those processes happening in the ocean are what drive not just the continents, but also the oceanic lithosphere. And so they all move together. The ocean and the continents are connected, the oceanic crust, I should say, and the continental crust, they're all connected and they get pushed or pulled in different directions. So that is our theory of plate tectonics, which is accepted today and has been for some decades. But Alfred Wegener did come up with this idea of Pangea, supercontinent, and the fact that it has broken apart and the continents have moved. Um, the oceans opening up, the Atlantic Ocean opening between North America, Europe, South America, and Africa. Something that we have a lot of evidence for today, which again, something that you'll go over in your lecture. The plate tectonic theory is considered a unifying theory because it explains so much in geology and earth sciences. Um, but what plate tectonics entails is plates uh, moving, these tectonic plates. And what they are the outer brittle part of Earth, solid part of Earth. And the outer brittle layer is the crust, but also a bit of the upper part of the mantle. They end up kind of sticking together a bit because they're both cold enough to be brittle, and um, that layer is called the lithosphere. Underneath it is the asthenosphere, which is warmer and can flow like a soft solid. I usually use the example of putty because putty is solid, but with enough pressure, you can deform it. Uh, you can squish it and cause it to kind of shift or flatten or flow. So in any case, the lithosphere, being the upper part, that is the tectonic plate. The rigid part, the outer part um, of the Earth. And there are many plates that make up Earth's surface. There's about 20 major plates, and we won't ask you to memorize any of them, or in lab we won't. Um, but the idea is that Earth's surface is made up of a couple handfuls of these um, tectonic plates or lithospheric plates, and they move. They move in certain ways and interact with each other. And so, in that way, we have three different types of plate boundaries, which is to say, um, there are three main ways that the plates move against each other. And so, one of the ways that plates move um, is that they will move away from each other. And so, in those locations where the plates are moving away from each other, we call that a divergent boundary. It's also called a spreading center or uh, spreading ridges. We do have a few different words for that, but the idea is that the plates are moving away from each other in those locations. On the other hand, plates can move towards each other, and that's what we call a convergent boundary. If two adjacent plates are moving towards each other, they are converging or colliding. And so we call the areas where two plates are moving towards each other convergent boundaries. And then there are places where two adjacent plates aren't really moving towards or away from each other. They are just essentially sliding past each other. Uh, and that creates a different kind of boundary. We call those transform boundaries, transform fault boundaries, because earthquakes are produced there. Um, but uh, yeah, there's no um, production of lithosphere or destruction, which does happen at divergent and convergent boundaries, which we'll talk about in a second. Something that's important to know for the lab um, is about stress, strain, and faults that are associated with each type of boundary. Now, I you probably haven't talked about stress, strain, or faulting in lecture yet. So, a little bit of background on that. Stress, you can think of it as a force that's being acted on the plates, on the rocks, on the land, or underwater. Um, stress, stress is like a force. So think of it that way. Some kind of force acting on the land. Strain is the effect that force has on the land. And then faulting, well, I'll get to faulting in a second. So stress and strain. Tension is associated with divergent boundaries, which is pulling something apart, right? If you're holding a rope or something and you pull your hands apart, you're trying to separate your hands and get them further and further. You're putting tension on that rope. And it's a similar thing with divergent boundaries, with the two plates moving away from each other, which we're seeing in this picture here. Um, there's one plate on the left, there's a second plate on the right, and this is separating them. This is the boundary between them, uh, with the plate moving to the left and the plate moving to the right. Um, so there is tension in the crust as these plates are pulling apart from each other, and tension causes stretching, right? If I'm pulling on that rope, maybe the rope doesn't stretch too much, but maybe I'm pulling on a rubber band instead. Then I can get a pretty good stretch on the rubber band by putting tension on it. Um, Convergent boundaries, on the other hand, we're looking at compression of the rocks, compression of the land, because two plates are colliding with each other. So if you are holding something between your hands and you squeeze it, you're compressing it. And that can cause shortening of the crust or whatever it is you're squeezing in between your hands. You're going to be making it smaller and shortening it. So that's our stress and strain at convergent boundaries. And then at our transform boundaries, we can see, again, here on one side is one plate. Here on the other side of this boundary is the second plate. And here they are with these little half arrows shown to be moving side by side and sliding past each other. The This is called shear stress, and it also produces shear strain. I always say this is the easiest one to remember, the shear stress and the shear strain, but people do tend to forget that it's the same type of stress and strain. They do describe slightly different things. Um, Shear stress, um, again, we have this side by side motion. Shear strain is hard to describe with just words, but it's like taking a sheet of paper and having your hands on two corners of that paper and then ripping the paper down the middle. That's kind of what shear strain is. Your hands are moving um, side by side and ripping that paper down the middle. That's shear strain. Now the faults, um, different types of faults are associated with the different plate boundaries. We have normal faults associated with divergent boundaries, reverse and or thrust faults associated with convergent boundaries, and transform and or strike slip faults associated with uh, transform boundaries. Now, what are these faults? This is what the faulting looks like for normal, reverse thrust, and transform faults. Um, I'm trying to get the pen because I'm going to draw something on here. Um, okay, so normal and reverse and thrust faults have what's called a hanging wall and a footwall on either side of the fault. Can't. Okay. And it's important to know which is which because that is how you determine if the fault is normal or reverse or thrust fault. So for me, I would get confused. I wouldn't remember what's the hanging wall or the foot wall. I would overthink it. And yeah, I confused myself. So, uh, where's the little? Okay, I can't even see it. Okay, so what I ended up doing is drawing a stick figure, and I would draw them going through the fault. Oops. And the feet always end up in the footwall side. Whoops. So feet and footwall. And then the head ends up in the hanging wall. And H for hanging wall, H for head, and obviously feet for footwall. And so this works no matter what type of inclined fault it is, normal fault, reverse thrust fault. So if I come over here and draw my stick figure through the fault, down there's the feet, and up here's the head. So that always worked for me. It's silly, maybe. It's simple, though. And yeah, so that's why it worked for me. So that's the first thing that you kind of need to do to determine whether something's a normal fault or a reverse thrust fault. Once you know what the hanging wall is and our fault is this break in the rock. That's what a fault is. It's rock that is broken and shifted and moved, which causes earthquakes. It's the movement of that um, rock that causes the earthquakes. But in any case, once you know where the hanging wall is, you have to determine, okay, has the hanging wall moved up or down? And so I see the offset of the land surface. And in this case, the hanging wall is lower than up here where the footwall is. And so in a normal fault, the hanging wall drops down. This is because the normal faults are being pulled apart. That's what these reddish arrows are. That's the tension. That's the tension that's in our divergent boundaries. Um, it's essentially loosening the friction that would hold the hanging wall and the footwall blocks together. Pulling them apart loosens that friction and allows the hanging wall to drop down the ramp of the fault. So that's why we have normal faults associated with tension, lengthening, uh, and divergent boundaries. It's that tension. Now, on the other hand, on the other hand, reverse slash thrust faults, the hanging wall here is up higher than the footwall. It has moved upward. And so that makes this a reverse and or thrust fault. It is because of the compression that the hanging wall is being pushed up the ramp instead of being allowed to fall down it. It is being pushed up the ramp. And so that is a reverse slash thrust fault. There is a difference between these two, reverse and thrust faults, but it's just the angle that the fault makes with the surface, and we don't need to worry about that right now. The reverse thrust, reverse faults are steeper. Um, but okay, yeah, reverse thrust faults, being pushed together like this, uh, that's compression, and it also causes a shortening in the crust as the hanging wall kind of moves up and up and up. The crust is getting, and the lithosphere is getting a little bit uh, shortened. And then finally, we have the strike slip faults or transform faults. You can use either term, where again, one fault block is moving one way. In this case, it's moving into the screen. This one on the other side of the fault is moving out of the screen. And that is what defines our strike slip or transform faults. There is no hanging wall or footwall here because most strike slip faults are vertical or nearly vertical. And so if you tried to draw a stick figure person, they would just end up bifurcated or split in half. So, yeah, we don't worry about hanging wall and footwall notations for the transform faults. But we are looking at shear stress and shear strain associated with these faults. So if I go back one slide, um, again, what we're looking at with divergent boundaries, tensional stress, stretching or lengthening as a result of that stress. And this happens in normal faulting. Compression, shortening, and reverse thrust faults happening under convergent boundaries, where again, one plate is colliding with the other. And then shear stress causing shear strain with strike slip or transform faults. So they're all related in that way. Okay, a little bit more detail about each of these boundaries. I'm not going to spend a huge amount of time here, uh, but divergent boundaries mostly are found in the oceans, and they cause seafloor spreading. That was the mechanism that allowed plate tectonics to become an accepted theory, discovering seafloor spreading, or in other words, uh, uh, magma rising to the surface of the ocean floor, the bottom of the ocean, and pushing the plates apart. That's seafloor spreading. The ridges itself, they are elevated above the abyssal plains, and this technically makes them mountains or mountain ranges. They're just underwater mountains. Um, However, they cut through um, all of our major ocean basins, and yeah, they create the divergent plate boundary itself. But we do also sometimes find divergence happening in rift valleys. So, rift valleys, places where there's a rift in the ground. Those rifts are actually faults, they're normal faults, and they can cause continents to split apart if we have great big long rifts in the land. Can eventually cause um, the continents to rip apart, which is what we think happened with Pangea. Great big deep rift valleys formed and eventually pulled Pangea apart. Um, or I should say pushed Pangea apart. Because eventually, when the continents rift far enough apart from each other, water starts to creep in, and that ends up producing seafloor spreading, which the magma that's pushing the plates apart, the magma also eventually creates new ocean floor. So there's a creation of new oceanic floor that's associated with divergent boundaries. It might look something like this, where the first figure we see a continent and it's starting to rip apart. The white arrows are showing movement apart from each other. Um, we see some rifting happening, then a true rift valley forms. And without getting into too much of the detail, the magma here is able to um, erupt at the surface a bit and still push the now two plates apart, or almost two separate plates, continuing to push them apart. And again, eventually, water is going to start to infiltrate and come into this deep rift valley. Um, meanwhile, the now truly two different plates uh, are moving away from each other while magma's creating true ocean floor. And then we get a very well established seafloor spreading uh, center, or a seafloor spreading boundary, a divergent boundary where magma is almost continuously erupting and causing the two plates and the continents now. We have oceanic lithosphere now attached to continental lithosphere crust. and all of it's being pushed over here. Oh, the oceanic floor and the continental crust is being pushed to the right. And over here, continent and the oceanic floor is being pushed to the left, all by that magma at the ridge. So again, this mechanism was pretty pivotal in the theory of plate tectonics. Convergent boundaries are just as important, though, especially where we have subduction zones. Subduction zones are where an oceanic plate sinks or is forced down below another plate. And there's a couple different ways to do this. One of the most common that we teach is an oceanic plate subducting beneath a continental plate. The oceanic plate is denser and much more readily sinks into the mantle or the asthenosphere. Continental crust, on the other hand, is less dense and it's too buoyant and it never subducts. As far as we know, it never subducts. Oceanic plate, however, is a different story. So, while the oceanic plate sinks into the mantle, um, it actually isn't melting until way, way, way deeper. However, we do develop magma anyway. There's a process called volatile addition that your lecture professor will tell you about. Um, but in any case, we do get magma forming, and there are volcanoes associated with subduction zones. Some of the oceanic continental um, volcanic arcs would be the Andes Mountains, which is in South America, the Cascade Mountains, which is on the west coast of North America, and the Sierra Nevada Mountains back in the day. They're not volcanically active anymore, but they were at a time in the past. So, an oceanic plate and a continental plate colliding, the oceanic plate subducts. We get a true subduction zone with volcanoes, and it might look something like this. This is the oceanic plate. Here it is running into a continental plate. The oceanic plate is subducting into the asthenosphere. We eventually have melting occurring, magma rising, and volcanoes forming here. There's deep subduction trenches associated with the subduction zone. But yeah, that's one type, one type of convergent boundary. There is also an instance where two oceanic plates can collide. And so one of them will subduct beneath the other. Which one, you ask? Whichever one is older, is how that goes. Because the older the oceanic lithosphere is, the colder it is, and the denser it is. So older, colder, denser, it almost rhymes. Two of them rhyme. The older, colder, denser plate subducts, whichever one that is. And we get magma forming and volcanoes forming in this case too, because these are subduction zones. However, the volcanoes are islands because we are in the ocean. So rather than volcanoes on land, we have volcanic islands. The Aleutian Islands in Alaska form this way. The Mariana islands, the Izu and the Bonin Islands, not just Mariana. The Tonga Islands are kind of down in the same area as the Mariana. They're a little south of the Mariana Trench. Um, so those are some examples of volcanic islands forming from an oceanic plate, which we can barely see any of in this figure. I don't know why they drew it like that, but this is an oceanic plate, and it is subducting beneath another part of an oceanic plate. It also happens to be attached to a uh, continental lithosphere, but this is oceanic out here. And these are the volcanic islands that are forming. They form parallel to the trench, more or less. They make a line of volcanoes um, that goes along the same direction as the trench. But that's what two oceanic plates colliding looks like. Older, colder, denser plate subducts, and we get volcanic islands. And then lastly, the convergent boundary um, that we haven't considered yet is two continental plates colliding. And so what happens is um, there may be subduction happening where the oceanic lithosphere is being subducted beneath one continent, but if those continents, if the ocean closes up, the continents will end up colliding, and neither one subducts anymore, right? We can't subduct continental lithosphere. Can't do it. And so the subduction stops, like gets plugged up. And instead, we have these massive mountain ranges, like the Himalayan mountains, where it's just continental crust crushing against other continental crust. And if it can't go down, it must go up. And it does. The Himalayan mountains formed this way. The Alps also formed this way. The Appalachian Mountains, uh, many hundreds of millions of years ago, formed this way. We think the Appalachian Mountains were as tall as the Himalayan mountains at a time. But in any case, we have convergence here, colliding continental crust, and huge, huge mountains forming in between. This is more what the process looks like and how the Himalayan mountains did form. The subcontinent of India, if I come over here on the right, it was pretty far out in the Indian Ocean. It was actually not too far from Australia at the time. But something happened. Um, we're not sure exactly, but something happened where India started just trucking it up north. It's really quite fast movement, geologically speaking, and it slammed into Asia. And so that would look like this. There was an ocean in between India and Asia. That ocean, the oceanic crust, was subducting beneath Asia. But when that ocean eventually closed up, right, it's like a conveyor belt, just kind of bringing India closer, 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 closer until they finally collided. And that's our continent collision forming massive mountain ranges like the Himalayas. All right, so our last plate boundary here, transform faults. As I've said before, the plates at these locations are just sliding past each other. We're not destroying any lithosphere, we're recycling it into the earth like we do with subduction zones. We're not creating any new crust like we do at divergent plate boundaries. Most of our transform faults are actually found in the oceans. Um, we're not going to get into that in our lab, just, I guess, sort of know that as a fact. Um, so yeah, they are part of seafloor spreading. There are, however, some transform faults that cut through land. One of the better known transform faults is the San Andreas. Um, but there's some others. The blanking the Anatolian fault. That's one. Um, and so those are transform faults that go through land. However, as I said, most transform faults are part of seafloor spreading. It's right in here, this section, right where the that laser pointer cursor is. You can see the white arrow on one side of the fault moving to pointing to the right, and this white arrow on the other side of the fault pointing to the left. And so that technically makes this section um, a transform fault. And you can see those black half arrows also pointing here to the left, here to the right. So that's just an example of a transform fault. And then lastly, here we have a world map. It looks a little busy, um, but we're essentially looking at major plates. And in black with the triangles, those are convergent boundaries. With no triangles, that's a transform fault. And these red thicker lines, those are divergent ridges. And then the arrows here, the blue arrows, show the relative motion of the plates. And so where we have a divergent plate boundary, these blue arrows are shown pointing away from each other because the two plates are moving away from each other. Same thing in the Atlantic Ocean here. These little blue arrows pointing away from each other because that's a mid-ocean ridge and there's seafloor spreading happening there. So those are just two examples with the blue arrows. The red arrows represent what's called absolute plate motion. And this is the direction the plates are actually moving. We have GPS sensors that we plant in the ground or in the seafloor, and satellites, same satellites we use for GPS. The satellites measure their movement, not just the direction of their movement, but their speed as well. And the longer the arrow is, the faster the plate is moving. So some plates are moving really fast, like the Pacific. Other plates, like Africa, Asia, not moving as fast. Um, but that is absolute motion. And if anybody needs uh, this absolute motion explained, I'm happy to meet virtually to explain that because mm, I don't know if I can do it uh, in email or just in words like this. But I'm happy to meet and you know explain something like this, why these red arrows are pointing more or less in the same direction, but we are still looking at a divergent boundary. Maybe I can try to explain. It has to do with the fact that the Pacific plate is moving much, much faster, And so it's kind of pulling away from the Antarctic plate here. Antarctic plate is moving pretty slowly, and so it's almost like it can't, even though it is technically moving this way, it can't catch up. And the Pacific plate is always pulling away from it. And so that does create a stretching or a divergence between the two plates. Like I said, I'm happy to meet in person to explain that. I have office hours on Friday too. You could stop by. But that's it for the explanation here. Um, we yeah, let me know if anyone needs any assistance. Other than that, the lab will be due next week, next Tuesday. Um, so yeah, please reach out if you have any questions.